Now we said that there is a phase relationship between current and voltage in an AC circuit, such that if the voltage, AC source voltage is delta V max sine omega t, current will be I max sine omega t minus phi, reflecting this phase difference. Now when I calculate the instantaneous power, that's the power delivered at time t, I multiply the current instantaneous value, I max sine omega t minus phi, with the voltage, delta V max sine omega t. So this will give me an instantaneous power, I max delta V max sine omega t minus phi. Now, you can recall that sine omega t minus phi is sine omega t cosine phi minus cosine omega t sine phi. So when I substitute that here, sine omega t sine square omega t cosine phi minus sine omega t cosine omega t sine phi multiplied with I max and delta V max. So this will be the instantaneous power. Now what we really care about is not the value of the power delivered at a certain point in time, but rather the average value of the power. So how do I calculate the average power? I take the average of this equality, so that is going to give me an average of sine square omega t cosine phi minus average of sine omega t cosine omega t multiplied with sine phi. Because these are constants, so they don't have, I don't have to consider their time averages. So what is the time average of sine square omega t? Now I know that sine omega t is a periodic function with a period t, so 1 over the period integral over 1 period, 0 to t, sine square omega t dt. Now cosine 2 omega t is 1 minus 2 sine square omega t. So for sine square omega t, I can substitute 1 minus cosine 2 omega t over 2. So now I can see that I will have dt over 2 minus cosine dt over 2. So dt over 2 integral will give us just t over 2. And the t evaluated between time 0 and 1 period will give me 1 period. So this will be t over 2. And minus 1 over 2 cosine 2 omega t dt, that will become minus 1 over 4 omega sine 2 omega t. But evaluated between 0 and time 1 period, sine 0 is 0, sine 2 omega t is also 0, because 2 omega is 4 pi over the period, so this would be sine 4 pi, which is 0. So I'm left with 1 over t multiplied with t over 2, so average value, time averaged value of sine square omega t is 1/2. What is the time average value of sine omega t multiplied by cosine omega t? Well, that's sine 2 omega t divided by 2. Sine 2 omega t is 2 sine cosine. So that is 1 over 2 period integral from 0 to 1 period sine 2 omega t dt. And the integral of sine is minus cosine. So we have minus 1 over 2 omega cosine 2 omega t, which is evaluated between 0 and time 1 period. Cosine 2 omega period is cosine 4 pi minus cosine 0. They are 1 minus 1, which is 0. So the average value of sine omega t cosine omega t is 0. So I can see that the average power is then, for sine square omega t average, I replace with 1/2. This with 0, so this will give me cosine phi over 2. So you can see that average power is I max delta V max cosine phi over 2. Since I max over square root 2 is I RMS and delta V max over square root 2 is delta V RMS, so the average power is I RMS delta V RMS cosine phi. So when we write the power in terms of the current that flows in the circuit and the voltage of the AC source, the RMS values, we have to introduce this factor cosine phi here. Cosine phi is called the power factor. Now, if you look at my series RLC circuit, the impedance I had calculated looking at this phasor diagram, remember, Z cosine phi is equal to R. Therefore, cosine phi is R divided by Z. And tangent phi was XL minus XC over R. So since cosine phi is R divided by the impedance of the circuit, this will be I RMS delta V RMS times R over the impedance. Now delta V RMS divided by the impedance is basically just I RMS. So this will be I RMS square times R. So the power delivered to the circuit by the AC source, the average power, I RMS delta V RMS, cosine of the phase angle between current and voltage, is equivalent to the power consumed by the resistor I RMS square R. So this is basically our result. So there are two ways to calculate the average power delivered. Now, if Z is equal to R, this will be purely resistive load and cosine phi will be 1 because phi will be 0. Then this will be just I RMS times delta V RMS. So you can see that the power delivered by an AC source to any circuit depends on the phase difference between current and the source voltage. This can be tuned by adding or removing capacitors and or inductors. So because cosine phi is something I can change by adding inductors and capacitance, that's something I can vary. Okay, let's look at an example. Calculate the average power delivered to the series RLC circuit described in the previous example. In the previous example, we had resistance R 425 ohms. The inductance was 1.25 henries before we changed the design. Capacitance was 3.5 microfarads. The frequency was 60 Hz for the AC source with a maximum voltage of 150 volts. And we calculated the maximum current in the circuit by calculating the impedance of the circuit. It was 0.293 amps. So this corresponds to an RMS current, maximum current 0.293 divided by square root 2, this is 0.207 amps, and the average power delivered to the circuit is equal to the power consumed by the resistor I RMS square times R, which is 0.207 square times 425 ohms. We calculate the average power to be 18.2 watts. Okay, so in this lecture we have seen that when we try to calculate the power in an AC circuit, we can do so for instantaneous power and average power. But when we report these values, really what we care about is the time averaged value of the power delivered to the circuit. The power delivered to the circuit instantaneous value is the instantaneous current I max sine omega t minus phi multiplied with the AC source voltage delta V max sine omega t. If we take the average of this power, because the time average of sine square is 1/2 and time average of sine times cosine is 0, we obtain 1/2 delta V max I max cosine phi. And 1/2 is 1/square root 2 times 1/square root 2. Basically, this is the product of the RMS values of current and voltage multiplied with cosine of the phase angle between them, where cosine phi is called the power factor. The cosine phi basically is determined by looking at the phasor diagram where we calculate the impedance. You can see for the series RLC circuit, we had tangent phi XL minus C over R, and Z cosine phi is R. So for cosine phi, we can substitute R over Z, and delta V RMS divided by Z is I RMS, so average power is also I RMS square times R. So if you don't want to calculate the phase angle, you can just use this result to calculate the average power delivered by the load to this circuit. When Z is equal to R, it's purely resistive and cosine phi becomes 1. And we can change the power delivered to the circuit by playing with the capacitors and inductors in the circuit, which will affect the value of the phase angle. So that's the lesson we learned. If we apply this to the previous problem, where we have used these values and the maximum current was 0.293 amps, all we should do is calculate the RMS current, which is done by dividing the maximum value with square root 2, and then the average power is just IRMS squared multiplied with R. So this gives us our average power, 18.2 watts.